all inversions.
Thank you.
There you go.
So hello, I'm going to present the work that we did to create an alternative way to do inversions that is compatible and simpler to use when doing dependent programming. So the goal is to have an inversion mechanisms that create readable and simple proof terms that can then be used to do reasoning on or to be understood when importing it as part of a library. Some examples of what it can be used for are that we created are transpositions of transposition of matrices prove that this transposition is involutive, or the example that I will that I will present here, which is manipulating finite sets following an idea proposed to us by Clément Pitt-Claudel. Can we switch? I'm going to start with a demo to show why we think this our method of inversion may be useful. Okay. So, to start with, I have a very simple type with 3 elements, RG and B, and I want a function that for each element returns a differently typed function. This is quite simply defined in Roc with dependent elimination. But now we want to do the same thing with fin of t.
It's still readable, so yeah, we'll just open. Don't have any epileptic people.
Yeah, I've go as is.
I can do that so that it's not technically full screen.
That's fine. Yeah, looks nice. Yeah.
Okay.
If it flickers, it flickers.
Yeah. Okay. So we want to do the same thing with fin of t, which when indexed, when specialized with an integer value, gives an inductive type with the given number of elements. So fin of 3 is a set with 3 elements in it. However, if we try to do the exact same functions as above using fin of 3, it doesn't work for 2 reasons. The first is that when doing the match, the matching will abstract over the number of elements n and not keep into memory that is 3. The second thing is that this technically is a shorthand for a nested match, and if we expand the nested match, in a match we must be we must present all constructors even when they don't have sense. If I have hexagon is fin t of 1, so only has 1 element, so there is no, so the successor of an element in fin of 1 doesn't mean anything, and we don't know what to put on the right. So what we propose is a new way to do inversion that changes the inductive type that is matched on, such that those 2 problems are solved. We see that if we have 0 elements in the set, we don't need to output anything, and that it's quite similar to the function just above that we wanted. To create those elements, we want 3 things. First, we want inductive types that are created from the original fin inductive type, and then translation functions that basically take the original object of type fin of t and transform it into our new inductive types, but keeping the information that we have only 3 elements. But one thing one might want to ask is, why bother? We already have inversion mechanisms in Roc. The first one that might come to mind is the inversion tactic. Well, if we try to use it for this, to define this function, when we say, well, first case is P1, it will say it will not work because the goal is P of X. Inversion does not take into account that as we are doing a pattern, a match on X, the goal should also change to reflect that to match the constructor that we are on. So what we need is dependent inversion. So let's use the dependent inversion tactic, which does not work because it has the same problem as the base match, in that it is trying to, it's abstracting over the value of n. One solution that does work and works very well is dependent elimination from the equations library. When we use it, we see that we have the correct three goals, P of F1, P of Fs of F1, and P of Fs of Fs of F1 corresponding to the three elements, and we can define the functions. However, when we look at what the, when we look at the function term that is created, we see that it's quite complex. It does work, so for most of the case it's enough. But for example, if you want to reason on it, we will need to use inversion tools. And if I were to import a library and print a function to see exactly how it works, I don't think I would be able to do so with that kind of definitions. So this is why we wanted to create our tool, our inversion method, whose goal is to create simple function terms. I will now go more into details into how exactly we create our inversion. Okay. So, as we saw, when eliminating over phi of t, we are abstracting over n. So what we want to do, what inversion does, is to constrain the value of the index n to be exactly 3. What historical methods like inversion, dependent inversion, or dependent elimination do is that they add the constraint in the form of an equality hypothesis to the conclusion, and through various means use it to eliminate impossible cases and restrain the possible values. As we saw, what we do instead is to change the inductive type that we eliminate on. We create a proxy type that mimics how phi of 3 works. And when eliminating it, as we are mimicking phi of 3 and not phi t of n for all n, we keep the information of the number of elements. So first, we want to create inductive types that can mimic this value. As we work with inductively typed indices, for example, 3, natural numbers in Roc are inductively typed. We only need to mimic what happens for each constructors, and at the end of the demo, match n times where n is the numbers of constructors we need, rather than specialize explicitly for 1, 2, or 3, or 27. So what we do is that we take the original inductive type and we see for its index what are the possible for each constructors, what are the possible forms that the inductive type can take. Here we see that the index of phi has a constructor S of n. So if our index has value 0, fin of t is empty. Then we mimic what happens for fin of s. If it's of the form s, it takes an argument which is n, which is the successee. Similarly, we as a parameter this index n. Then we want to we are specifically in dependent inversion. This is why inversion tactics didn't work. We want our goal to follow the case analysis we are doing on X. So we need to add into our inductive types we need to add back what structures the original object had. So the constructor applied to the same arguments. Once this is done, we can create a function that will separate that will compute which partial inductive type we are in, depending on the constructor, on the value of our index. And then we can create a translation function that for each constructor of our initial inductive object, we translate it to the corresponding constructor in our partial inductive types. Then it's the simple matter of using it, destroying it using match or the destruct tactic in interactive mode to use this new inversion. If you don't want to bother remembering each, you don't want to remember that you named the object FinProxy, you can use type classes for non-dependent or dependent inversion to bypass this problem. So in addition to this technique, we have created a systematic algorithm that allows for the creation of those partial inductive types, which works by successfully refining the inductive types through transformations. Most of them are administrative transformations that we use to simplify specializations, which is the creation of the partial inductives themselves and of the translation functions. Note that if we need to invert on multiple indices because multiple indices hold informations, or if we have deep patterns where constructors have arguments that are themselves themselves hold information, we can repeat this step by creating partial inductive types of partial inductive types to take that into account. So as a conclusion, we are working simultaneously with this inversion method on creating a plugin using MetaRock that creates those definitions automatically so that they can be used easily. We are exploring edge cases that are present in the transformation, most notably when doing specialization. And we are working on case studies, for example, with Concert to see if we can replace the use of the inversion tactics in those projects with our proxy-based small inversions, on if there are gains of doing this. Future work is mainly adding support on edge cases. For example, if the index that we want to invert on is itself dependent, not all of its constructors will be present, and we will need to invert it first to be able to invert our original object. Some nonlinear patterns can cause problem and necessitates partial injectives that are not the standard one that we can directly derive. So we are working to generalize our methodology to work with them, and with the eventual goal to publish this plugin either as a standalone or as its use is also based on type classes, while trying to integrate it within the equation plugin.
Yes, thank you very much.